So in this lecture, I will present some properties of the conditional expectation. So the first property, P1, it's that the conditional expectation is linear. So here, I will be working always with a probability space omega fp, and I will assume that we have a sub-sigma algebra G. So G, it's a sigma algebra which is contained in F, and I will represent now the functions by x and y instead of f and g. So these are random variables, so functions from omega to r, which are f measurable. And my first claim is that if you take two variables, random variables which are integrable, so let's say that x, j, dp, it's finite, then the conditional expectation of x1 plus x2 given g, that this is equal to the conditional expectation of x1 given g plus the conditional expectation of x2 given g. So I want to prove this condition. So let's prove that. Of course, if x1 and x2 are integrable, then the sum is integrable. And here I have a candidate, which I will call z, and I want to show that z is equal almost surely to the conditional expectation of x1 plus x2 given g. So in order to prove this identity, I have to prove that z fulfills the two conditions of the conditional expectation. So recall, the first condition is that z is g measurable, but z is g measurable because this conditional expectation is g measurable, and that one is also g measurable, and therefore the sum is g measurable. So z fulfills the first condition. So now let's recall the second condition. For the second condition, I want that for all set B in G, the integral of z on the set B, it's equal to x1 plus x2, the integral of x1 plus x2 on B dp. So I want to prove that this identity holds for all B in G. So let's prove this identity. Let's recall what z is. So I'm starting from the left-hand side, and I will replace z by its value. Its value is a sum, so it's x1 given g plus the conditional expectation of x2 given g dp. Now, we have seen that the conditional expectations are integrable. Therefore, I can use the linearity of the integral to write that as b, the conditional expectation of x1 given g dp, plus the integral over b of the conditional expectation of x2 given g dp. Now, since this is the conditional expectation, by the second property of conditional expectations, this is equal to the integral over b of x1 dp. Right? This is by the second property of the conditional expectation of x1 given g, and the same thing for the second term. And now I can use the linearity of the integral to get that this expression is equal to the right-hand side. So we started from the left-hand side, and we arrived at the right-hand side. So we proved this identity. Therefore, z fulfills the two conditions of the conditional expectation. Therefore, z, it's almost surely equal to the conditional expectation, and this is what we claimed. Let me just say that the same proof shows that if I take, and that I leave you as an exercise, so if I take alpha a real number, then the conditional expectation of alpha x1 given g, it's equal to alpha, the conditional expectation of x1 given g, And this is essentially the same proof. Actually, in a while, we will prove a much more general identity. Now let me prove the second property. The second property tells me that, well, if x1 is less or equal than x2, then the conditional expectation of x1 given g is less or equal than the conditional expectation of x2 given g. And I won't recall, but I'm always assuming that these random variables are integrable. So let's prove this property. And actually, by linearity, it's enough to prove that if x is non-negative, then the conditional expectation is non-negative. Right? Because, well, you just subtract x1, so you have that x2 minus x1, it's non-negative. You use this property, and you use the linearity of the conditional expectation to get the result you want. So let's prove this. Well, I know that b, the conditional expectation of x given g, dp, that this is equal to b x dp for all b on the set, on the sigma field G. So now let's take a special set B. B will be the points omega such that the conditional expectation it's less or equal than 0. So since the conditional expectation is G measurable, B is indeed a set, and let me call that 0. B0 is indeed an element of G. Now, let me use this identity to say that the indicator function of the set B0 times the conditional expectation integrating dp, that this is equal to the integral over B0 or x dp. Since by assumption x is non-negative, this integral it's non-negative. On the other hand, this random variable, it's negative. It's non-positive because the set B0 is the set of all points in which this is negative. So we have a non-positive number less or equal than 0 multiplying 1 or 0. Therefore, this product is less or equal than 0. And since its integral is larger or equal than 0, it has to be equal to 0. So from this, we conclude that B0, the conditional expectation of x given g, dp, is equal to 0. Because so let me repeat, on the one hand, it's positive, and on the other hand, this function here, it's always negative, and therefore its integral has to be negative, so it's at the same time positive and negative, so it has to be 0. And since this function here, it's negative, less or equal than 0, and its integral is equal to 0, we conclude from measure theory that this function is equal to 0 almost surely. And this means that, the set of points at which this function is negative or less or equal than 0 has measure 0. So that implies that since this set has measure 0, this means that P of B0 it's equal to 0, right? But B0 is the set in which it's non-negative, so this means that the conditional expectation is positive, right? If this is equal to 0 almost surely, well, either it's equal to, or either this conditional expectation it's equal to 0, or on the sets in which it might be different from 0, then this set has to be 0, so therefore it follows from this product that the set B0 has measure 0. So here's the third property, and this one will be used many times. It's a generalization of what I said before. So now let's assume that we have x, which is integrable, and y, a random variable. So x is measurable with respect to f, while y, it's measurable with respect to g, and I'm assuming also that x, y is integrable. So x is integrable, and x times y, it's integrable. And so since x times y, it's integrable, I can take the conditional expectation of xy given g. And what I claim is that since y, it's integrable, that this is equal to y times the conditional expectation of g. So at the beginning, I proved this property when y is a constant. Of course, if y is a constant, xy is integrable and y belongs to g. So this extends greatly what I mentioned before. So this is a very important property of the conditional expectation, which will be used many times. And my claim first is that, well, it's enough to prove this property for x and y non-negative by using linearity, right? You can always write x as x plus minus x minus, y as y plus minus y minus, and now we write xy as, since x is integrable, this means that these two, x plus and x minus, are integrable. Since x and y, it's integrable, this means that x plus, y plus, or x plus, y minus, and so on, that all combinations are integrable. Now, I can come to this identity, replace x by this difference, y by this difference, use linearity, which we already proved, and to remain with only positive terms. So we will have x plus, y minus, x plus, y plus. So now if we prove this result for non-negative variables, we'll have that identity. And here we can, to the right-hand side, you can apply, again, linearity to obtain this identity at the end. So indeed, by this representation of x and y and by linearity, it's enough to prove this identity for non-negative random variables. So let's assume that these variables are non-negative. And again, I have here an object, z, which I want to prove is the conditional expectation of xy times given g. So I want to prove that this function here is indeed this conditional expectation. And to prove that, I have to prove two properties of the conditional expectation. The first one is that z is g measurable, but that's clear because y, by assumption, is g measurable, and the conditional expectation, by definition, is g measurable, so the product is g measurable. So z fulfills the first condition. So now it remains to check the second condition. The second condition is to show that if b belongs to g, then we have that the integral of b of z dp, that this is equal to bxy. So this is what we have to prove. And so z, what is z? Z, it's the conditional expectation of x given g times y dp. And we have to show that this is equal to the integral over b of x, y dp. So this is the identity we want to prove. And we will prove that in steps. First, let's assume that y is the indicator of a set A, for A in G. If y is the indicator, here what I have is the indicator of y, the indicator of A, times the indicator of B. That will give me the indicator of A intersection B. By definition of the conditional expectation, this is equal to the integral of A intersection B times x, and this is exactly B times x times the indicator. So maybe let me write that. So here we have B, the conditional expectation of x given G, times y, but y is the indicator of A, dp. So this is equal to the integral of over A intersection B times the conditional expectation. Now since A and B belongs to G, A and B belongs to G, the intersection belongs to G. So by definition of the conditional expectation, this is the integral of A intersection B x dp. And, well, by definition of y, this is the integral of over B of x, the indicator of A dp, but this is y. So this identity holds if y is the indicator of a function. That's very nice, so we proved the first step. I hope you're convinced. Now I can use linearity to extend it to y simple function. So if y is equal to the sum from j from 1 up to n of a constant cj times the indicator of a set aj, provided all aj belongs to G, or measurable with respect to G. So by using linearity of the conditional of the integrals, I can extend this identity from indicators to simple functions. So just by linearity of the integral. And now, since I assume I want to extend that to non-negative functions, since I assume that y is non-negative, I can obtain a sequence yn of simple functions which increase to y. So yn are simple functions, and they increase to y. So this identity by step 2 holds for simple functions. So what I have is that, let me write it here, because the proof is almost done. So by step 2, what I know is that B, the conditional expectation of x given G yn dp, this is equal to B, the conditional expectation x given G, not x, not the conditional expectation, but x yn dp. Now, we know that I erased, but we know that x, it's non-negative. We proved that in this case, the conditional expectation of x given G, it's also non-negative. And therefore, if yn, it's increasing to y, xyn, it's increasing to xy. And by the monotone convergence theorem, so this, I'm using the monotone convergence theorem, this is increasing to b x y dp. In the same way, yn is increasing to y. This means that this product is increasing to y times this conditional expectation because it's positive. So the left-hand side converge by the monotone convergence theorem again to the conditional expectation of x given G, y dp. Since for all n, these two objects are identical, we have this identity. And therefore, we have also this identity for all y, g measurable, which are non-negative. So indeed, this inequality holds, and therefore, the function z fulfills the two conditions of the conditional expectation, and therefore it's equal almost surely to the conditional expectation of xy given g. So as I said, this property is very important and will be used in the following many times. So now P4, which tells us that the absolute value of the conditional expectation of x given g, that this is bounded by the conditional expectation of the absolute value of x given g. So let's prove that. Well, let's write x as x plus minus x minus. So let's replace x by x plus minus x minus. Let's use the linearity of the conditional expectation to write that as the conditional expectation of x plus given j minus the conditional expectation of x minus given g. So we hand up to this point that the left-hand side here, it's given by this difference. Now let me use that this difference, it's bounded by the absolute value of x plus given g plus the absolute value of x minus given g. Now remember that since x plus it's non-negative, the conditional expectation it's non-negative, almost surely. The same thing for x minus, and therefore this is actually equal to the conditional expectation of x plus given g minus plus the conditional expectation of x minus given g. Let me mention once again that all these steps are almost surely. So when I say that, well, this is equal to that, this means that almost surely that's equal to that this inequality holds almost surely, and so on. But since we have always a finite or a countable number of steps, we can take the union of all steps in which this is true and still have a set of measure 1, and therefore obtain the statement almost surely, so which is valid in a set of full probability. So here I can again use the linearity, so this is equal to x plus x minus the conditional expectation of this quantity given g, and this is the absolute value. So indeed, the absolute value of the conditional expectation, it's bounded by the conditional expectation of the absolute value. So let me now prove the conditional monotone convergence theorem, which states that if you have a sequence xn of random variables which are increasing to x, and remember here I'm assuming that all these variables are integrable, then what I claim is that the conditional expectation of xn given the sigma field g also increase to the conditional expectation x given g. And so let's prove that. So what I claim is that we can assume without loss of generality that these random variables are all non-negative. And this because you can always take xn minus x1, and since the variables, the sequence it's increasing, this variable is non-negative, you call yn equal to xn minus 1. Of course, yn increase to x minus x1. So if now you have a sequence yn, which is non-negative, which is increasing to x minus x1. So if you can prove this result for non-negative random variable, what we will conclude is that yn given g, it's increasing to x minus x1 given g, if we can prove this result for non-negative increasing random variable, which is the case of yn. Now, you can use linearity to conclude the result for xn, because yn it's xn minus x1 given g. So this is increasing to this random variable, but by linearity, this is the conditional expectation x1 given g minus the conditional expectation of x1 given g. And the same thing on the right-hand side. On the right-hand side, this expression is the conditional expectation of x given g minus the conditional expectation of x1 given g. Since this sequence is increasing to that one, adding this conditional expectation on both sides, we conclude that indeed the conditional expectation of xn is increasing to the conditional expectation of x. So it's enough to prove this result in the case in which the random variables xn are non-negative. So let me assume that xn is non-negative. Since we know that since xn is less or equal than xn plus 1, we have seen that the conditional expectation of xn given g is less or equal than the conditional expectation of xn plus 1 given g, which means that this sequence of conditional expectation is indeed increasing. And since it's increasing, it has a limit. So let me call z the limit. We also know that since the random variables are non-negatives, that these random variables are non-negative. So let me call z the limit of the conditional expectation of xn given g. And our claim is that z is equal to the conditional expectation of x given g. This limit exists because we have seen this sequence, it's increasing, and therefore it has a limit, and this limit is non-negative. So what remains to be shown is that z is indeed the conditional expectation of x given g. To prove that, we need to show two things. The first one is that z is g measurable, but indeed these conditional expectation, so these random variables are g measurable, and therefore the limit is z is g measurable. And second property is that for all b in g, the integral over b of z dp, it's equal to the integral over b of x dp. So let's prove this identity. So by definition, z is the increasing limit of these non-negative random variable. So since the conditional expectation of xn given g, it's increasing to z, if I multiply on both sides the indicator of b, we have that this sequence is increasing to that one. This is an increasing sequence of non-negative random variables. Therefore, I can use the monotone convergence theorem to say that this integral, it's increasing to the integral over b of z dp. Now, since b it's an element of g, the integral of the conditional expectation of xn given g on b, that this is equal to the integral of xn over b. And now xn is increasing to x, it's non-negative, so I can use again the monotone convergence theorem to say that this expression is converging to bx dp. So bx dp is equal to this limit it's equal to this limit, and this limit is converging to that expression. Therefore, these two integrals are equal, and this is exactly what we wanted to prove. And this completes, therefore, the proof of the conditional monotone convergence theorem. So now, P6, this is the conditional Fatu lemma. And here it reads as follows. So let's consider xn a sequence of non-negative random variable, let me assume that the limit imp of xn it's in L1, so it's integrable. Then what I claim is that the conditional expectation of the limit imp of xn given g, that this is less or equal than the limit imp of the conditional expectation. So just keep in mind that I'm always assuming that these random variables are integrable. And here I'm assuming that the limit imp of xn belongs to L1, so it's integrable, just to make sense of this conditional expectation. We define the conditional expectation only for random variables which are integrable, and therefore this is why I need this condition. So let's prove this result, which is based on the monotone convergence theorem, the conditional one. So let me define by yn as the infimum for k larger than n of xk. So since these random variables are non-negative, yn is non-negative, and yn it's increasing because I'm taking the infimum on less and less number of random variables. So this is an increasing sequence, and therefore yn converge to the limit imp of xk. So we have seen in the conditional monotone convergence theorem is that if I have a sequence yn of integrable random variable, yn it's of course integrable because it's non-negative and it's bounded below by xn, and therefore it's integrable. So we have a sequence of increasing integrable random variables converging to the limit imp. So by the conditional monotone convergence theorem, we know that yn given g, it's increasing to the conditional expectation of the limit imp of xk given g. So let me write it here. The limit imp of xk given g, it's equal to the limit in n of the conditional expectation of yn given g. But now, as I already observed, yn it's larger or equal than xn. I'm sorry, smaller, less or equal than xn, because it's an infimum. So by the monotone property of the conditional expectation of yn given g, it's less or equal than the conditional expectation of xn given g. Therefore, the limit of the sequence, so we have a sequence of random variable which is bounded by the other one. So this means, since this limit exists, that the limit in n it's less or equal than the limit imp of the sequence conditional expectation of xn given g. And therefore, we just proved that this limit it's less or equal than the limit imp of the conditional expectation of xn given g. And this is exactly what we wanted to prove. So that proves the conditional Fatu lemma. So property P7, it's the conditional dominated convergence theorem. Which can be stated as follows. Yeah, you consider a sequence xn of integrable random variables, and you assume that they are uniformly bounded by a random variable y, which is non-negative and integrable. Now I claim that the conditional expectation of xn given g converge to the conditional expectation of x given g, and this happens in L1 and almost surely. So let me first show that it converges in L1. You see that x is, of course, okay, I forgot to say that here I'm assuming that xn is converging to x, of course. So you have a sequence xn, which is uniformly bounded by an integrable random variable. Xn converges to x, and what we claim is that this implies that the conditional expectation of xn is converging to the conditional expectation of x. So you see that what I was saying, x is in L1, it's integrable because since xn converges to x and xn are bounded by y, the same happens to x, which shows that x is indeed integrable. So I want to prove first the convergence in L1. So let me write the expectation of the conditional expectation of xn given g minus the conditional expectation of x given g. And I want to prove that this converges to 0. Well, by linearity of the conditional expectation, this is equal to the absolute value of the conditional expectation of xn minus x given g. So here we use linearity. Now we are going to use the fact that the absolute value of the conditional expectation is bounded by the conditional expectation of the absolute value. Therefore, this expectation is less or equal than the expectation of xn minus x given g. Now remember that the expectation of the conditional expectation is equal to the expectation. So this is equal to the expectation of xn minus x. And now, since xn is converging to x and xn is bounded by y, so we can use the dominated convergence theorem to say that this is converging to 0. So that xn is converging to x in L1 by the dominated convergence theorem, and therefore we proved our first claim that this sequence is indeed converging in L1 as we claimed. Now let's prove that the convergence happens also almost surely, and for that, so now second step, convergence happens almost surely, and for that we will use Fatu. So let me first define a new sequence, which is y, let's say, plus xn. So since xn is bounded by y, this is certainly positive. So we have a sequence of positive random variables, and Fatu, the dominated Fatu, tells us that the conditional expectation of the limit imp of this sequence, y plus xn given g, that this is less or equal than the limit imp of the conditional expectation of y or xn plus y given g. Right, this is a sequence of non-negative random variable because the absolute value of xn is bounded by y, and therefore by Fatu we have this inequality. Note that the arguments are exactly the same as for usual dominated convergence theorem or Fatu. So now, of course, the limit imp of this quantity, so let me rewrite the left-hand side. So the limit imp of this quantity is equal to y plus the limit imp of xn given g. And by linearity, this is equal to the expectation. Well, but note that xn is converging to x, so the limit inf of xn is actually x, and by linearity, this is equal to the conditional expectation of y given g plus the conditional expectation of x given g. So this is the left-hand side. So now let's use linearity on the right-hand side to rewrite that as the limit inf of the conditional expectation of xn given g plus the conditional expectation of y given g. And now we can subtract the conditional expectation of y given g on both sides. This is a random variable which is integrable, and so we can subtract to obtain what our first conclusion is, that the expectation of x given g is less or equal than the limit inf of the expectation of xn given g. And now I will repeat the same argument, but instead of using y plus xn, I will use y minus xn. So this is also a non-negative random variable. So let's see. We can use, since y minus xn it's non-negative, we can use Fatu again to say that the limit inf of y minus xn given g is less or equal than the limit inf of y minus xn. So now let's see what happens on the left-hand side. So the limit inf of y plus xn, this is y plus the limit inf of minus xn. But the limit inf of minus xn, it's minus, well, okay, so here since xn is converging to x, minus xn is converging to minus x, and the limit of minus xn, it's minus x. So what we get here, it's just a minus sign instead of a plus sign. So let's see on the right-hand side. On the right-hand side, we have, we argue exactly as before. So we have here, by linearity, this is the expectation of y, and this is lim inf of minus the conditional expectation, and we can put the minus outside, so we can rewrite this as the conditional expectation of y given g minus the limit sup of the conditional expectation of xn given g. And at this point, we can just subtract as before the conditional expectation of y given g on both sides to get that minus this conditional expectation, it's less or equal than minus that one. So multiply both sides by minus 1 to get that the limit sup of the conditional expectation of xn given g, so this is this, it's less or equal than the conditional expectation of x given g. And now by looking at this formula, what you get is that this conditional expectation, it's less or equal than the limit inf. Of course, the limit inf, it's less or equal than the limit sup. The limit sup, it's less or equal than that quantity. And since these two quantities are the same, we get that the limit inf, it's equal to the limit sup. So there exists a limit, and this limit, it's equal to that quantity. And this is exactly what we wanted to prove. So we wanted to prove that this convergence holds almost surely. And this is it. Now, property P8, this is the conditional Jensen inequality. So we have phi defined on R to R, a convex function. And we want to prove that the conditional expectation of phi x given g, it's larger or equal than phi of the conditional expectation of x given g. And to make sense of this conditional expectation and that one, we require that x and phi of x are integrable. So let's prove this inequality. The proof is also similar to the usual Jensen inequality, and here we will appeal to the existence of a right derivative. So let me represent by d plus phi of x, the right derivative at x of phi. So this is this limit, the limit of as h decrease to 0 of phi x plus h minus phi of x divided by h. So I claim that this limit exists at all points. So I leave it to you to check that d plus phi exists and that it's monotone. So if x is less or equal than y, then d plus phi of x it's less or equal than d plus phi of y. And finally, so let's say that if you have a function, a convex function like that, so you see that here up to this point the derivative will be just equal to that. So if you take the linear function which it's equal to, let's say at this point it's equal to phi of x, and it's linear and with coefficient given by the right derivative, this linear function, it's always, of course here it's badly drawn, it's always below. This means that if I take the linear function which at a point, so let me call here, let me fix a point x0, and let me consider a linear function L of x, which is equal to, let's say, a plus bx. So I want b to be d plus phi at the point x0, and I want L of x0 to be equal to phi of x0. This means that I can rewrite this function L of x, and it depends, mind, on x0. I can rewrite it as f phi of x0 plus d plus phi at x0 of x minus x0. So this is the linear function which is equal at x0 to phi of x0, and whose linear coefficient is given by the right derivative of phi at x0. Well, the third property of this function is that L of x, it's always bounded, so let me write it x0, it's always bounded by phi of x. So I leave it to you to check that such a derivative exists, that it's monotone, and that it satisfies this property, which is the one I wrote there. So let me write this here at phi of xi0 plus d plus phi at x0 times x minus x0, it's less or equal than phi of x. And this holds for all x0 in R. And so our proof will start from this inequality. I will just replace in this inequality x0 by the conditional expectation of x given g, and x by the random variable x. So by replacing x0 by this conditional expectation, x by this, what we get is that phi of, or maybe let me place phi on the other side. So this tells me that d plus phi of the conditional expectation of x given g times x minus the conditional expectation of x given g, that this is less or equal than phi of x minus phi of x0, which is phi of the conditional expectation of x given g. Okay. So at this point, what I would like to do is to take the conditional expectation with respect to g on both sides and argue as follows. Well, if I take the conditional expectation of this expression, this one, it's measurable with respect to g, so it gets out from the conditional expectation, and by linearity, this conditional expectation, it's equal to 0. Therefore, on the left-hand side, I would get 0. On the right-hand side, I would get the conditional expectation of x given g minus, well, this is g measurable, so its conditional expectation, it's equal to itself, minus phi of the conditional expectation. And that would give me this inequality. The problem is that this expression, which appears here, if I want to consider its conditional expectation, I need to make sure that this expression is integrable, because we only define the conditional expectation for objects which are integrable. And there's no reason for this expression to be integrable. So I need to perform some cutoff, and this is what I will explain now. So let me define lambda as the set of omegas in our space omega such that the conditional expectation of phi of x given g, it's bounded by a. So let me fix a, and let me denote by lambda of a the points in which this conditional expectation is bounded by a. So of course lambda, and I won't keep a, lambda it's an element of g. And let me define y to be x times the indicator of the set lambda. And let me repeat the same argument, but instead of using x, I will use y. So I will reach the conclusion that this expression here, that this inequality holds for y instead of x. So let me rewrite this inequality. We will have that d plus of phi computed at y x chi, but since lambda it's g measurable, you see that the conditional expectation of y given g, it's equal to the conditional expectation of x given g times chi a, chi lambda. So this is the first term, and then let me write it as y minus the conditional expectation of y given g. And this is less or equal than phi of y minus phi of the conditional expectation of y given g. Now mind, since I'm multiplying this conditional expectation by this characteristic function, this expression here, it's either 0 if that conditional expectation is larger than a, because we will be out of the set lambda, or it's equal to the expectation, but in that case the expectation will be bounded by a. So this expression here, it's bounded by the supremum of d plus between minus a and a. And therefore, since, well, d plus, as we have seen, it's monotone, it's bounded, this expression is bounded by the two extreme values, and it's finite. It's just a finite quantity which depends on the value of the derivative of phi at minus a and plus a. Here we have y, but y, it's x key a, so this is an integrable function because x, it's assumed integrable. And here also, this conditional expectation is the conditional expectation of x given g, which is also integrable. So this expression here, it's integrable, while this one, it's bounded. which means that this expression here is an integrable function. So I'm allowed here to take the conditional expectation on both sides. Here I'm allowed because I'm assuming that, so I have to show that phi of y it's integrable. I will do that in a second. And here this is clearly integrable because this is phi. Okay, so I'll show that these two expressions are integrable in a second, but let me take the first the conditional expectation on both sides. So by taking the conditional expectation on both sides, since we have seen that we are allowed, at least on the left-hand side, to take the conditional expectation, this expression, the first expression here, it's G measurable, because this is a random variable G measurable, and lambda, it's a set which is G measurable. So that gets out from the conditional expectation, and here I get the conditional expectation of this term, which is 0. So by taking the conditional expectation, I will get that this is bounded by the conditional expectation of phi of y given G minus phi of the x given G times key of lambda. And here, when I take the conditional expectation, since this object is G measurable, this is equal to this expression. So in order to complete the argument, I have first to show that this expression here, it's measurable and integrable as well as this one. So that this one, it's integrable, is clear because on the set lambda, this conditional expectation, it's bounded by A. So this expression here, it's bounded by, it's a number between, value between minus A and A. Phi, it's bounded in this interval, so this expression, it's bounded, and indeed, being bounded, it's integrable. So there is nothing to worry about for this term. For that term, well, let's see, I have to show that phi x chi lambda, it's integrable, but what is that? Well, on the set chi lambda, this is phi of x. And I assumed that phi of x is integrable. And on the complement, well, so we are in the complement, so this is 0, and therefore this is phi of 0. So we see that this object, it's equal to a random variable which is integrable because this is bounded by 1 and this by assumption is integrable. This is a real number which multiplied the indicator function. So this expression, it's indeed integrable, and therefore the right-hand side is an integrable function, so I'm allowed to take the conditional expectation, and when I take the conditional expectation, what I get is this difference. So up to this point, we proved that this inequality holds, and so let me write that as phi of the conditional expectation of x given G times chi lambda. It's bounded by the conditional expectation of phi chi x chi lambda times x given G. Now I will remember that this set lambda depends on A. So what I will do is I will let A tend to infinity, and I will use the previous theorems on dominated convergence or theorems for random variable. So this random variable here, it's bounded. So phi x chi lambda, I erased it. I shouldn't have erased it. It's bounded by phi x plus phi of 0. So it's indeed dominated by a random variable which is integrable, so I can use the dominated convergence theorem. And when I send a to infinity, this is converging. So when I send a to infinity, this is converging to phi of x. So by the conditional dominated convergence theorem, as a tends to infinity, this expression is converging to the conditional expectation of phi x given g. While on the left-hand side, well, this is fixed, and this is converging to 1. So this expression is converging to this phi of the conditional expectation. And so this is converging to phi of . So here I'm just using the fact that as lambda is increasing, as a is converging to plus infinity, chi of lambda is converging. So this is integrable, so therefore as a converges to plus infinity, this set is converging almost surely to omega. It contains almost all points, and therefore this is converging just to this expression, and therefore from that inequality we finally get Jensen's conditional inequality. Now let me state the Schwartz conditional inequality. So I'm taking two random variables, x and y, such that x squared it's finite, and the expectation of y squared it's finite. So both have a second moment, and what I claim is that the conditional expectation of x, y given g square, that this is bounded by the expectation of x squared given g times the expectation of y squared given g. All these conditional expectations are well defined because I'm assuming that x and y have finite second moments, so x squared is integrable as well as x times y. So my first claim is that the random variable x squared divided by the conditional expectation of x squared given g, that this is integrable. So let's prove this inequality. What could be a problem is that while this conditional expectation could be equal to 0 in a certain set, and so we would be dividing by 0, but what we'll prove is that actually if this is 0, x squared is also 0 on that set, because this is actually integrable. So let's prove that this is integrable, and we will use the monotone convergence theorem to do that. So this is a positive random variable. So we can use the monotone convergence theorem to say that this is equal to the limit as epsilon decreases to 0 of the same expression but now in which I'm adding the indicator function of the set in which this conditional expectation is bounded below by epsilon and bounded above by 1 over epsilon. This is, since x squared it's integrable, this is an integrable random variable, and therefore if I let epsilon to 0, this set it's increasing to a set of full measure, and therefore by the monotone convergence theorem we have that indeed this integral it's equal to this limit. This is just the monotone convergence theorem. Now I will do the following. Well, this is an indicator function, so it's equal to its square. And so here I'll put it at a set B epsilon, where B epsilon is exactly that set. So it's the set at which epsilon it's bounded by the conditional expectation of x squared given g, bounded by epsilon minus 1. So there is no difference between this integral and that one. Now I will use the fact that B epsilon, it's g measurable. And here I have a random variable z, which is integrable because, well, on this set this is bounded and x squared it's integrable. Therefore, this random variable z, it's integrable, and what I know is that this set z dp, that this is equal to B epsilon, the conditional expectation of z given g. Well, and since this expression it's integrable e z, which is x squared x given square given g given g, right? That object it's integrable, x squared it's integrable, and therefore we have seen that this conditional expectation it's equal to, we can, since this is measurable, g measurable, and this is g measurable, we can take them out from the conditional expectation, and this will be 1 over the conditional expectation of x squared given g, the indicator of that this conditional expectation it's bounded between epsilon and 1 minus epsilon times the conditional expectation of x squared given g. So this is a previous result. We have x squared, which is integrable. X squared times this expression, it's also integrable. Therefore, we can use the result that y z given g, it's equal to y conditional expectation of z given g if y is g measurable and if z and y times z are integrable. This is exactly the situation here, so I can use that previous result. And in this case, what I will get is that this conditional expectation is equal to that expression times this conditional expectation. At that point, you see that these two expressions cancel, and actually, this conditional expectation becomes just the indicator function. So what we proved is that this is equal to the integral over B epsilon of the indicator of the same set. And now, well, I can remove B epsilon because B epsilon, it's exactly this set. So this is equal to the same expression without B epsilon. And again, as epsilon goes to 0, this set, since this set it's integrable, it's going up to a set of measure 0 to the old set omega, and therefore this is converging to this is increasing to 1. So by the monotone convergence theorem, we concluded that not only this random variable is integrable, but that its expectation it's equal to 1. Well, now we are ready to prove that inequality. So let me rewrite x divided by, so let me take the square root of this expression. So this is integrable, and therefore the square root it's in L2, and in particular it's integrable. And the same thing for y. And let me use the following inequality. We know that 2 times ab, that this is bounded by a squared plus b squared. So I'm using this inequality here. So let me multiply that by 2 and say that this is bounded by x squared divided by, so sorry, I forgot to write the square root. So by this inequality applied to a, which is given by that, and y given by that, it's bounded by that. Now I will take the conditional expectation given g on both sides. So this is an integrable function, and x squared, it's also an integrable function. So when I take the conditional expectation with respect to g, this gets out from the conditional expectation by the property of conditional expectation which I mentioned earlier, and what remains is that the conditional expectation of x squared given g divided by the same quantity. So after taking the conditional expectation, I get 1 here and 1 here. So let me repeat that. So here, just to remember, I'm using this property, that this is equal to y z given g. And what are the assumptions I need in order to have this identity? Well, I need z to be in L1 to be integrable and yz to be integrable. So what's playing the role of z here is this expression, and it's indeed integrable, and y, it's 1 over this expression, and we have seen that x squared divided by this expression, it's also integrable. So I'm allowed to use that property, and once I rewrite, I place here the conditional expectation to move this out from the conditional expectation, and then I will remain with the conditional expectation of x squared given g divided by the same quantity, therefore I get 1. And here I get 1. In the same way, when I'm taking on the left-hand side the conditional expectation, I can move these two expressions out of the conditional expectation and get that this quantity, it's equal to the conditional expectation of x y times g divided by the square root of the conditional expectation of x squared g times the conditional expectation of y squared times g by using the same property. And therefore, we have a 2 here and we have a 2 on the right-hand side, so this is bounded by 1, and this is exactly the inequality which we wanted to prove. So let me insist here what the property I'm using, as I mentioned, is here, but now z, the random variable z, which I'm using here, it's xy. So xy, it's indeed in L1 because x and y are in L2. And y, it's 1 over the square root of x squared given g, expectation of y squared given g, square root of that, and xz times y, which is xy divided by this expression. It's also in L1 because x squared divided by this expression without the square root, it's in L1, and y squared divided by this conditional expectation without the square root is in L1. Therefore, zy, it's also in L1. So we are using again this property, and we are allowed to use it because both z and yz are integrable. Therefore, we are allowed to use that property, which permits us to move out of the conditional expectation these square roots. So the denominator can be moved out, and once it's moved out, what remains is this expression, and therefore we get that inequality, and this is exactly what we wanted to prove. So the last property of this lecture is the following. So let's say that z, it's a random variable which is integrable, and let me take two sigma fields, G1 contained in G2, and what we want to prove is that if you consider the conditional expectation of z given that G2, so this is a random variable which is now G2 measurable. Now if I take this conditional expectation with respect to G1, what I claim is that this is equal to the conditional expectation of z given G1. So let me prove this identity. So let me call that y. Oh, yes, let me call that y. And my aim is to prove that y is equal to this conditional expectation. So in order to prove that y is equal to that conditional expectation, I have to prove two properties of y. I have to show that y is G1 measurable, and then I have to prove that for all b in G1, the integral of y over b, it's equal to the integral of this random variable over b. So we have to prove that these two property holds in order to show this identity. So that y it's G1 measurable follows from the definition of this conditional expectation. This conditional expectation is G1 measurable, therefore y it's indeed G1 measurable. So now we have to prove the second property, fix b in G1. We have to show this identity. Well, let's look at the left-hand side. By definition of y, this is the integral over b of the conditional expectation of z given G1. And now, since b is in G1, by definition of this conditional expectation, this is equal to the integral over b of z dp. So this is the left-hand side. Now let's look at the right-hand side. Well, b belongs to G1, but G1 is contained in G2, so b belongs to G2. Since b belongs to G2, by definition of this conditional expectation, this is equal to b z dp. And therefore, indeed, we have that the left-hand side is equal to the right-hand side because both are equal to the integral of z over the set b with respect to p. And this proves this identity. Mind that this is, of course, also equal to the conditional expectation of z given G1, conditional expectation given G2. So this means, so let me first comment about these identities, and then I will prove this identity. So this means that if we have an ordered two sigma fields, one contained in the other, we can essentially exchange the order of the conditional expectation. We can take first conditional expectation in G1, then in G2, and actually they are equal to the conditional expectation with respect to the smallest one. Well, why this identity is true? Well, because this object here, it's integrable, because z is integrable, and it's G1 measurable. But if it's G1 measurable, it's also G2 measurable. And we have seen that if we have a random variable which is G2 measurable, then it's equal to its conditional expectation. And then this proves that identity. So with this, I conclude this lecture. I really recommend you to do the exercises because this is a very important subject in probability, and to get familiar with this subject, you have to do exercise. So I really recommend you to do the exercises in the notes.